Hello students, this is an NPTEL online certification course on advanced microwave guided structures and analysis. Myself Professor Bratin Ghosh from the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. The first lecture today will be on the scattering matrix concepts. So, let us go straight away to the lecture material. So, we all know at microwave frequencies the concept of voltage and current is no longer good. We have to instead use the concept of voltage and current waves. Okay. So, we talk of reflection, we talk of transmission of waves, and in order to characterize this reflection or transmission of waves, we formulate this mathematical language of scattering matrix. So, this concept of scattering matrix enables us, unlike at low frequencies, to characterize the phenomenon of reflection and transmission of waves in a microwave network. So, let us look at a typical microwave network, an N-port microwave network. So, here V1 plus, V2 plus, Vn plus are respectively the incident voltage waves on port 1, on port 2 and port N respectively. Okay. So, there are intermediate ports, port 3, port 4, whatever may be, and similarly the reflected voltage waves from at port 1 is V1 minus, the reflected voltage wave at port 2 is V2 minus, and the reflected voltage wave at port N is Vn minus. So, in order to characterize this environment, we use the scattering matrix, and that relates the incident and the reflected voltage waves in the network, in the N-port network. So, this constitute the left hand vector constitutes the reflected voltage waves from at port 1 through port N, and then we have the scattering matrix. So, the left hand side, as I said, denotes the reflected voltage wave, that is equal to the scattering matrix times the incident voltage waves. So, this is the mathematical description of this circuit. Now, we attempt to find out the properties of such a scattering matrix. What are the relationship between the elements of the scattering matrix? Towards this end, we first develop the formulation towards that. So, for that we first define under a normalized environment the voltage and current waves, which is the total voltage wave is given by the incident voltage plus the reflected voltage. The total current wave is given by the incident current minus the reflected current. And because of the normalization, the normalized voltages and currents are related by V plus by I plus equal to Z0. This is the characteristic impedance. It must, however, be remembered that the total voltage and by total current is not equal to Z0. This must be remembered. So, it is only the forward voltage by the forward current and the backward voltage or the backward current, they are related by this expression, but not the total voltage and total current waves. And because of the normalization, so this Z0 becomes 1, so that we can write it as V plus minus V minus. And from these two equations we get this is very easy, half V plus I and similarly V minus is half V minus I. So, therefore, there is no necessity of including the current wave inside the formulation, because the current is given in terms of the voltage waves V plus and V minus, and therefore, the total circuit or the total network, characteristics of the total network can be represented in terms of V plus and V minus. Now, consider a situation where this is a transmission line and this is an old terminal plane in which I have measured my scattering matrix, and I want to translate this to this new terminal plane. Okay. So, in this scenario we can relate the voltages at the voltage waves at the old terminal plane with that in the new terminal plane, and that this frequently arises because S11 or any kind of scattering matrix parameters can be measured at a particular terminal plane, and I may want to translate it, I want to derive the equivalent scattering parameters at another transmission at another terminal plane. So, this is very simple to understand. So, theta n is the electrical length of the line with this is the ln is the physical length. So, theta n is the electrical length of the line corresponding to the physical length of ln. So, these two relationships can be easily written because Vn and Vn plus they differ by a phase of e to the power minus j theta n. So, S n n dashed is the scattering matrix at the new terminal plane. So, it is related to V n minus dashed by V n plus dashed. So, that can be related to the V n minus and V n plus at the old terminal plane. So, this can be written as S n n So, this gives the relationship between the S matrix, the S n n prime at the new terminal plane and the S matrix or the S n n at the old terminal plane. So, this is a frequently used relationship everywhere. Then we come to the symmetry of the scattering matrix. We prove that the scattering matrix is symmetrical. So, my voltage wave is total voltage wave is V n plus V n minus. My total current wave is I n plus and I n minus, that is equal to V n plus minus V n minus, because we are dealing with a normalized system as previously. So, therefore, I can write the voltage matrix as V minus, that is equal to Z times I, because V is equal to Z I. So, V is the summation of the incident voltage and the reflected voltage, that is equal to Z times I, and I is nothing but I plus and I minus. So, that is equal to V plus minus V minus. Okay. So, from which the relationship between V minus and V plus, where S is given by we call this equation 1. So, S is given by Z plus U inverse times Z minus U. Okay. So, where U is the unit matrix. We also have label this as 1. So, we also have, so let us write this also. That we saw previously, that V plus equal to half of V plus I, and V is equal to nothing but Z I. So, you can write this as similarly, we know V minus as half V minus I, and that is equal to half of okay. From which I can relate V plus and V minus, and V minus is equal to okay. And from there we can write the equivalent S matrix as, because V minus equal to S V plus So, we can write the S matrix as this. That is very clear from here. So, we call this equation 2. So, then from 1 get the transpose of S So, we can get the transpose of S as this quantity. So, these matrices are symmetrical matrices, the Z matrix and the U matrix. So, therefore, the transposes of these matrix are equal to the original matrix. So, I can write that as So, now if I compare this with 2, if I compare this with 2, equation number 2, we see that they are equal. So, let us say this, comparing with 2, we get S transpose is S, and which means that the S matrix is a symmetrical matrix. All right. So, this is the first characteristics of the S matrix. So, we will continue after this.